So here's another video I want to talk about displacement. Here we have the motion of we're throwing at our object, a ball or a water balloon, say out of a second-story window, the same sort of motion that we looked at before when we were doing motion diagrams. I've reproduced the graph here, and I've identified four specific points in time of interest where we were looking at the position function before. One at t is equal to 0, where the object is initially launched. T is equal to 3/4 of a second here at the height of its trajectory. The position vector at 1.5 seconds and the position vector at 2.25 seconds. And so I want to evaluate the displacements between each of these position vectors. So before I do that, just to help, again, some notation, I'm going to call r sub 0 to be the position vector at t is equal to 0. I'm going to call r sub 1 to be the vector at 0.75 seconds, r sub 2 to be the position vector at 1.5, and r sub 3 to be the position vector at 2.25. Numbering vectors like this is often common, and as long as you keep track of what's going on, this is perfectly fine. And so the first thing I want to do is calculate the displacement between the first two vectors. And so in calculating a displacement, that means we have some initial and final time, and so my initial time in this for my first displacement will be 0. My final time for my first displacement is 0.75 seconds, and so the displacement delta r, and I'll call this delta r1, it's the first one that I'm going to calculate then, is going to be r1 minus r2. I'm sorry, r2 minus r1. It's the final. Oh, no, I had 1, of course. 1 is right. Minus 0. So this is my final vector, which is r1, and this is my initial vector, which in this case is r sub 0. And I'll call this delta r sub 1. That's the first one I'm going to calculate. It's a common type of notation. Okay, so if I want to do this graphically, I'll start with this vector, and I'll sort of reproduce it over, sort of translate it over here. It looks like I'll need more room than that. Translate it over here. It's coming off in that direction. And then what I'm going to do is I have to subtract from it our initial vector, which is r sub 0. So subtract, I need to find this vector in the opposite direction, put its tail at the tip of the first one, and then the resulting vector starts from the tail of the first to the tip of the second. So this is delta r1. And as we saw from before, the displacement vector then points from the location on the position diagram of the tip of vector 1 to the location of the position diagram of the tip of vector 2. So this displacement vector, delta r sub 1. Okay, all right. So now I want to calculate delta r sub 2, the displacement vector between the next two vectors, the next 2 points in time. And so this would be r sub 2 minus r sub 1, or the vector evaluated at 1.5 minus the vector evaluated at 3.4. So let's just do this graphically first. So if I try to translate r sub 2 over here, I get vector that looks like that, and then I have this minus the vector at 3/4, and so if I want to turn it in the opposite direction, put the tail at the tip, and then go down, I have something that looks like this. So this is r sub 2. This one is negative r sub 1, and I add 2 to negative r sub 1 using the graphical method. And so the result then goes from the tail of the first to the tip of the second. And so this is which I described as a displacement delta r sub 2. And again, on the motion diagram, we see it starts from the position of vector 1 and points to the position of vector r sub 2. Okay, we'll do one more here. And if we look at now delta r sub 3, this next displacement, we wanted the displacement between the vector r3 minus r2. What am I saying here? What I'm saying is a displacement assumes you've chosen two specific points in time, which in this case is t is equal to 2.25 seconds and t is equal to 1.5 seconds. I've put those times into my position function, and from my position function I've identified two vectors, which in this case is the vector r evaluated at 1.5 and the vector r evaluated at 2.5, and those vectors are represented then by these two yellow arrows. Those are the vectors function evaluated at those two times. Then the displacement then is the difference between those two, the later time minus the initial time. Okay, so let's do that. If I would take graphically, I have now r sub 3, which is this kind of long, almost horizontal arrow, and then I take r sub 2 minus r sub 2, which is the same length in the opposite direction, and then I put the tail of it to the tip of the first one, and then my resulting vector goes from the tail of the first to the tip of the second, and this is delta r sub 3, usually just over the 3, and then if I put that on the position diagram, it points from the tip of the first one to the tip of the second one. There's delta r sub 3. So there we have we calculate the displacements for these particular points in time. So you notice I did not choose each successive point in my initial motion diagram. I chose every third. And so, again, a displacement is simply defined between some initial and final time position, and you can choose whatever time is necessary. And so as long as you're specific, then you will be able to do the calculation correctly. The important thing that I'm trying to get at is we've introduced quite a bit of notation. Here we've gone to the numbers instead of the letters, and we have a lot of symbols flying around. As long as you remember the verbal definition of what displacement means and the process necessary to calculate it, then you're not going the different notation you might see on any given problem or any given book won't confuse you. Okay, there's a final important part of displacement I want to talk about. And so to do that, let's go to the same trajectory, the same motion diagram for the same system, only in this case we have a different coordinate system. And so the different coordinate system leads to different position vectors, and we saw this before. But so let's go ahead and calculate our displacements. So if I want to calculate delta r sub 1, which I called r1 minus r0, and I'm defining these in the same way. R sub 1 is this r evaluated at 3/4 of a second. R sub 0 is the vector function evaluated at t is equal to 0. All right. So in this case, if I want to calculate this difference, I'm going to have r1, which now points like this, minus r sub 0. R sub 0 is the 0 vector in this, if you recall, for this position function. So that means that delta R1 is simply equal to R1, because our initial vector is the 0 vector, so something minus 0 is just itself. Okay? Fine. Let's go to the next one. And so here I want delta, the next displacement is going to be R2 minus R1. So R2 for this in this coordinate system is a straight line along the x-axis, and then that's probably a little long. Try to make it somewhat reasonable. I'm sort of doing this by eye. And so now I want to subtract from that R1, so that means you add the negative. The negative is the same magnitude pointed in the opposite direction, and so then I take the tail of it, put it at the tip of the first, and then the resulting vector goes from the tail of the first to the tip of the second. This is delta R2, and we see then on the motion diagram it points from the first point on the motion diagram to the second, or the tip of the first vector to the tip of the second. This is delta R2, delta R1. And so then finally, if I want to calculate delta R3, which is the third vector minus the second vector that I've identified here, this one was R2, R3. If I do that graphically, now I have this long vector that points off at an angle. There's R sub 3. And now I want R sub 2 in the other direction of the same length. Its tail starts at the tip of R3. And then the resulting vector goes from the tail of the first to the tip of the second. This is delta, what I've called delta R3. This is R sub 2, and we see that back on the motion diagram, this vector goes from the first point on the motion diagram to the second, or the tip of the first vector to the tip of the second. And in there, I mean the tip of the initial to the tip of the final, which for this displacement vector was R sub 2 and R sub 3. The procedure is, again, always the same regardless of the words you use or the notation that you use, and that's the displacement depends on 2 points in time. You calculate the position vectors for those 2 points in time, and then you subtract them, subtract the first from the second, and that gives you the displacement vector, which points from the first point on the motion diagram to the second. Okay, the final thing to note that is very important from this is if you look at delta R1, R2, and R3 in this picture, and delta R1, R2, and R3 in this picture, they are exactly the same. Which means displacement does not depend on coordinate system. Big red letters. That's a clue. That is a clue that this is important. I can't get my eraser working here. Does not depend on coordinate system. I had two steps for the same trajectory, and I'm looking at the same points in time, but measured in 2 different coordinate systems. This is my first one, and my position function is different in the 2 cases. If you look at the yellow vectors here, 0 and the 3 yellow vectors, compared to the 4 yellow, and then here the 4 yellow vectors, those vectors are very different. But the displacement vectors between them are identical. So the displacement does not depend on the coordinate system.